Welcome back from lunch. A little smooth introduction back to where we were. There's different mathematicians that have contributed to our current standing on contact and symbolic topology. And there's essentially three schools I can think of that have very rich history. And one is the Russian school, Arnold and company. The other is the Schiff school, stratified school that came out of McPherson in the US. And there's also the French tree. So at least today I want to just give a couple of minutes of the French tree, and then we can talk about other parts of the tree some other time. So first fun fact, I guess Euler everybody does know. Well, we keep talking about Lagrangian, so I thought, well, let's start there, up there, when he was the one like writing about that. And then you just go down math genealogy, and you want to get to the people that you know and love like these days, like, who are alive and active. And the names are somewhat familiar. So Lagrange goes to Poisson, which a little bit about Poisson geometry has a lot. Then there's Michel Charles. I don't know if you ever do it, but if you go to Paris, these are three names that appear in the Tour Eiffel. In the Tour Eiffel, it's a monument to science and engineering. So there's names of scientists and engineers all around, and you can see Lagrange, Poisson, and Charles. So they were all there. And then we go down here, and well, I don't know, we keep talking about the Darboux theorem. So Gaston Darboux was his time. And then it was Emile Borel, maybe not in congruency flighting, but pretty prominent person, Paul Mundell, and then we're down to Cartan. So who cared a lot about the geometry, more in the differential setting. And from Cartan, we get to John Searle. And this is the guy who started studying Morse theory in a parametric version, the person who proved the isotropy theorem. Those diagrams are named after him. And he had a student, Francois Salonenbach, and he's emeritus, but he's extremely active and fantastic member of the French community in Nantes. Since we're talking about the job market, I owe my sort of big break in Europe thanks to Francois. He invited me, I still don't know why, to give a seminar in Nantes. And when I was a grad student, I just went there and I just talked about some very cute linear algebra computation I had done with the quaternions. For some reason, he liked me, and he emailed Emmanuel Giroux that you gotta invite this guy. And then suddenly, Giroux invited me, and suddenly I was just going around seminar after seminar. I really owe him a lot. And then he had two students, Jean-Claude Sicolat and Claude Viterbo, and they really contributed a lot to the generating function or generating family theory. Lisa is an exponent of the US sort of branch in generating families. And really more recently, in conjunction with Guillermo, Claude and Stéphane Guillermo have really developed the theory of microlocal sheaves a lot. And Stéphane actually came from another lineage of mathematicians, coming from Pierre Shapira, who during his PhD, right after his PhD, did collaborate a lot with Kashiwara. And they both wrote a big book on the microlocal theory of sheaves. So that was in the late 80s, 90s. In 1982, they already had a draft. And all the ideas of microlocal theory come from Mikio Sato. So that's sort of Japanese branch. And then these two collaborated. And then in France, it wasn't exactly Shapira, but it was somebody very close to Shapira introduced the hyperfunction theory. And then that's how the things developed. Right. So, by the way, does anybody guess what happened right in 85, 82, what happened in the 80s? Gromov came and said, oh,
Yes.
this is how you do it. And sort of the sheep were sort of not as prominent for a while. But many years later, Kashiwara, Shapiro, and Guillermo, and I'm going to talk about a theorem of them three in 2016. So that's 30 years later. They revived the sheaf theory that for a while had been lost. And they proved exactly that this is an invariant of lambda. So that's a theorem of 2016. So look at the dates. Think about what Gromov did to your garden. All right. Okay, so we have this category that we named. So those are sheaves on M. In our case, M is R2 that are singularly supported on our lambda. And you want to think of that as being something that's invariantly defined under Legendre isotopies, more generally contact isotopies. I say more generally, it's kind of equivalently. So any Legendre isotopy can be realized through a contact isotopy. So let's at least down to earth, with the description from this morning, try to understand why would that be the case. And then I'll explain the more general state. So first of all, suppose you have a sheaf like this one. So you have a sheaf in here, and it has some stocking here A, some stocking here B, and the sheaf, for now, we're just gonna have some map from A to B. So again, now I'm implicitly using the description this morning, the post-set descriptions through exogamy, that James also talked about. Now you go and you perform a Rademeister 1 move. So as said in the first lecture, this is one of the instances of allogeneic isotopy. And now the new sheaf, well, it should be, whatever you do, it should be relative to the boundary. So A should still be here, B should still be here. So everywhere in here should have A, B, B. And now you ask yourself, like, what should I add in here so as to make this invariant? So if this is to be a Lagrangian invariant, I should be able to compute the category of sheaves for this Lagrangian lambda 0 in here, oriented downwards, it's lambda 0. And then after performing the Lagrangian isotopy, I should be able to somewhat map in an equivalent way this category to this category. So at least at the level of objects, let's understand what that does look like. Okay. So in general, you're going to have like some kind of formula for these, and you can do it by hand. So actually what's going to happen is that you compute the conditions as James did. So the cone is going to give you a condition. It's going to give you that this map and this map should be such that whatever object question mark you put in here, that complex should be a cyclic. So what should it be? Well, A maps into B in two different ways. So the way to make that a cyclic is to put just the cokernel of that map. So in here, you're going to put the question mark will be the cokernel of a certain maps out of here. I want to give an example which is slightly more subtle. Like suppose for a second that you have K downstairs and 0 upstairs in here. And now you do a Lagrangian isotopy and you're trying to fill a sheaf which is K downstairs, 0, 0. What do you put in here? So this should still be fine. But now any vector space I put in here is going to give me the short exact sequence. K goes to 0 direct sum 0, goes to question mark. So how could that be a cyclic? So I want everybody to think of this, or I mean, you're welcome to think of these as, for me, the simplest instance where the word derive is necessary. So if you were just talking about sheaves of vector spaces, without ever saying the word complexes of sheaves or sheaves of complexes of vector spaces, if you don't use the word complex, you're going to go awry, and you're exactly going to go awry in here. There's no vector space that you can put here, concentrated in degree 0, that's going to make this thing a cyclic. So the answer is that in here, you're going to put K shifted by some quantity, such that when you take the hypercohomology of this complex, understood as a complex of complexes, then there's going to be a diagonal map that connects these two people, and that has a chance of canceling. Does that make sense? So why you're not doing like just vector spaces and everything? Why do you insist on saying DG or DG derived or something like that? Well, already the Rademeister move tells you should be working in that world of complexes. Does that make sense? Okay, so that's a very explicit instance of how invariance does work. I strongly recommend that you work through the other Rademeister moves. So say you have this situation in here, and now you go and move somewhere like that. So here I'm going to have some regions A, B, and C. Those regions stay here. A. Now there's going to be still B, it's going to be still B, and now C. So the really interesting new region is this new region in here, question mark. And so what is this going to be? So in this case, kind of similar to below, what you're going to end up having is there's a map from B to C. There's a map, if I orient the right way, from B to A. And then what you're going to be putting in here is actually also the cokernel of this map. So that's something that, at least at the level of linear algebra, it can be named and it all works. Okay, so that's an example of a Rademeister 2. And now I want to do one example of a Rademeister 3. I could also tell you more generality how to do these formulas, but I want to do a very explicit kind of example. So I will do this Rademeister 3 and try to understand this very geometrically in terms of lines and planes in 3 space. So let's say we have a sheaf that we start having 0 here. That's something we declared. In examples, this is going to happen a lot. And then every time we go up by one of these arrows, we go up exactly by 1. So later in this lecture, I'm going to talk about the microlocal rank, and this is saying that the microlocal rank is 1. So here we're going to have K and K. Here we're going to have K squared, and here we're going to have K cubed. So here there's K squared. And here, if you think about it, the thing here going from 0, it's also going to happen. So the diagram is exactly like that. So we have this k going into this k squared, and then k cubed, and k cubed. One way to think about this is the following data. First, I read this diagram, 0, k, k squared, k cubed. What this information is giving me, all the maps being injective, is it's giving me a configuration in K3, which is given by the origin, 0, a line, a plane containing that line, and then K3. So it's a line through the origin, that's this map, K to K squared, and then a plane containing line through the origin, that's the map from K squared to K cubed, and everything is happening here in K cubed. That data, by the way, is called the data of a flag in vector space. A nested sequence of subspaces increasing something by 1, line, plane, the whole thing. Now, every time that I cross one crossing in here, every time that I get this crossing, there's another flag that I can consider. Like the second flag that I could consider is past this crossing, I can do this. Now, what is the shift singular support condition telling me? Well, here they're going to coincide exactly, right? So the second flag is going to have exactly the same plane. But what is this telling me? The crossing condition tells me I have 0 k k k squared. This needs to be a cyclic, so this needs to be isomorphic to the direct sum of these two. So these two lines need to be different. So now the second information of the flag is necessarily a different line. That line is different than the green one. And that gets me there. Does that make sense? Okay, now you continue. What is the next thing that you can do? The next thing that you can do is take the flag that goes like this. Now it goes this way, and then you go like that. Does that make sense? So here, what is this flag? The flag keeps the same line as the red, right? Because this line is keeps the same line. So here the crossing condition. Now I've crossed this crossing in here, right? So now I have k squared goes to k cubed, k squared goes to k cubed. So the condition that k squared plus k squared is isomorphic to k cubed modulo this line, it's saying that whatever plane I choose, it has to be a plane that is going to direct some modulo the intersection. So it's going to be a different plane. That's like kind of a blue plane, different than the green and red, but it's going to be the same line as the red. So that chooses a blue plane through this line. Does that make sense? And finally, when you take the last one, it's going to be the same plane, but now you choose the line differently in that plane. Does that make sense? Okay, so just randomized tree says exactly these 4 pieces of data, these 4 flags in there. Obviously, if you think about it, they're completely determined by like initial and final flags, but I mean, we're maybe talk about it now. Okay, so now you do this randomized move, and what's happening? Well, the only place where this is happening, then the only difference is this new region. So this initial flag that I had here on the left, that's still going to be the same, the flag that went this way. The flag that's at the very end, the flag that went this way, it's still going to be the same. So the only difference is happening exactly at this level. And here in the middle, what happened is that I had this line, which was different. It was the red line, which was different from the green, but still containing the grid plane. So now question is like, what should I put in here? Well, it's still going to be k, so 0, k, k, and now we're going to have k squared. And now in here, you're going to have the k cubed, k squared, and k squared. So what are you seeing here, the difference? The difference is I used to talk about 3 lines, k, k, and k, 2 planes, k squared and k squared, and 1 total space. And out of that, I created 4 flags. Now the information is slightly different. It's 2 lines, 3 planes, and you get the k squared. So any guess for how to say functorially did you go from here to here?
Take duals.
Yeah, essentially you're taking duals. So now instead of that, just take the duals of everything else, and that's going to determine that. So it's a very nice kind of polar dual version in linear algebra of what this randomized 3 moves do. I tend to like these sort of flag descriptions, and starting tomorrow, we're going to be using this kind of description. All right, so now I'm going to talk about foundational results kind of from a high-end viewpoint, like general theory. But again, when it comes to Legendre knots, you're perfectly welcome to just compute through linear algebra via the exothermy description. And you're going to have a proof of invariance in the same way that Shekhanov proved in 2000 that the DGA was invariant for nuts. He just went and computed. He didn't describe some model of disks or anything. He said, well, it's invariant under Rademacher moves, I'm done. Well, in the same way, in 3D, you can do it by hand. Now, if you ever tried, you try to classify the Rademacher moves in higher dimension. Well, they increase in number. That to me is not a problem. The problem is that they increase to infinity, and that to me is a problem. So if you look at Arnold's book, Singularities on Caustics and Wavefronts, there is some descriptions for the Rademachers in dimensions 2, 3, 4 for the Legendrian, but there's a point in which it becomes completely intractable. There's infinitely many things that can happen. It just doesn't look good. So this kind of combinatorial method would not work. And the theorem is for saying, so this is the invariance theorem. So this was proved by Guillermo, Kashiwara, and Shapira. Yeah, as I mentioned, Kashiwara earned the Abel Prize, or was awarded the Abel Prize recently. And Shapira was collaborating with Kashiwara in the 70s, and Guillermo was a student of Shapira. And a short version of the statement is, so I'm going to do the short version, and then the longer one is that sheaf lambda of M is invariant under Legendrian isotopies. So in particular, is a Legendrian invariant. But any decent Legendrian invariant, any invariant in this world, you shouldn't just say, oh, it is equivalent when I do an isotopy. You actually will like some kind of canonical map that has something to do with the isotopy. And that
M is scalar too.
their theorem is arbitrary. So yeah, so for us, I'm going to use I've been using MR2, and starting tomorrow, I'm going to use M equals R3. Their theorem is true for any analytic, any smooth manifold. Okay. So what is actually the statement? The statement is that, in fact, given a contact isotopy, so for any contact isotopy, and this is a family of contactomorphisms in the unique cotangent bundle. Again, think of them R2, they're not comparable otherwise. These are contactomorphisms. This guy, like T around between 0 and 1. There exists, this is the important part, there exists, and I'm going to write it in a slightly different color, but in appropriately understood way, unique sheaf kernel. So for now, I'm just going to call it sheaf kernel, and then we can discuss what the word kernel means here. It does not mean kernel as in kernel of a linear map. It means kernel as in the kernel of the Fourier transform. Which are different. So it exists in a unique sheaf kernel, K sub phi T, that depends on the isotopy, so that's depending on this guy. And where is this a sheaf on? This is a sheaf on M times I. So I is exactly this interval times M times 0, 1, such that now I'm going to write two kind of quick sentences. The first one is the singular support of this guy, singular support of this sheaf is exactly given, so is contained into the graph of this phi t. So maybe something that I have not explained a lot, but maybe let's take it. In the same way that the graph of a symplectomorphism is a Lagrangian, in fact, it's even only if, the graph of a contactomorphism is a Legendrian. So for each fixed t, you have a Legendrian, and as you trace those Legendrians, you get another Legendrian. Okay. So as a very example to keep in mind, think of this Legendrian as being the first one. As I do a Rademacher move, there's going to be a moment in which I start to grow like that. And I can think of this, movie, you can actually think of it as a Legendrian dimension 1 more, and that's exactly the Legendrian whose front is given by the swallowed there. Okay, so each of these phi t's for a given t has a Legendrian graph. I can put them all together. I'm going to get a front, and that itself is a Legendrian. And that's exactly the graph of the isotopy phi t. Okay, which is Legendrian. Okay. And now the second part, which is the one that implies legendary invariance, convolution with this sheaf kernel gives you an equivalence. So let's be precise with that. So kernel phi t convolution dot. It's something that goes from sheaf lambda to any isotropy applied to it. So from sheaf lambda m to sheaves phi sub t of lambda m. I'm going to describe this functor in a second, but this is an equivalence. The way they proved it, the techniques they used was about derived categories, the way this whole thing is built, and the way the convolution works. Everything can be defined in the DG's enhancement. So the proof is actually the same one. Okay, so what is this functor? This is sometimes called a convolution. And I'm going to write the functor first, and then we can discuss it. So given a sheaf F, you do the following thing. This manifold where I'm here, this was supposed to be a sheaf on m times 0, 1. So fix a t. So for each fixed t, so this t is fixed now. So fix a t in here. And then you're going to get this map, for instance, t equals 1, and map you from there to there. Does it help if I write t equals 1 instead? Maybe that's slightly clearer. Got that. After time 1, it will go from here to here. So I have two projections. I have the projection, so for time equals 1, I have the projection onto the first m, and I have the projection onto the second m, right? So call the projection on the first m p1, the second is p2. So what I can do is, if I think of these as the initial m, initial n times 0, I can pull back this sheaf under the projection. So now this is going to lift the sheaf from m up in here. Now I can multiply by that guy. So now you tensor with this sheaf k of phi 1. And now there's a sheaf upstairs, which you now push forward in here. So now you take p2 and then push forward over here. Okay, so let's start to make comments about this formula. So everything should be derived if you want things to be derived. So derived tensor product, derived direct image, so on and so forth. Now, what is this trying to say sort of effectively? So the analog of that, it might be helpful, is the following. This is going to be extremely stupid, but might be helpful. Suppose you have a function on variable x. This is a one-dimensional function with one guy. And you want to obtain another function that is kind of very different with on the variable y. So call this like g of y. And x and y have kind of nothing to do with each other, in a way, okay? So one way that you can think about it is if x is inside of capital X and y is inside of capital Y, is you can take the product x times y, so take x times y, and what you could do is find inside of here a function which is like k of xy. And now what can you do? Well, you can say, you can literally think about this being R. So I have a function on one variable, I want a function on one variable, and I have a function in two variables in here. What you can do is you can think of this function as still being a function on this space where the variable y is never used. That's exactly what this piece of the equation is doing for you. That's what the pullback does. Think of this as being here, completely ignoring that. Okay, the tensor product, here you would just multiply those two functions. So the tensor product in here, now the analog would be you take f of x, and you multiply it by k of xy. And then maybe the most interesting geometric operation is when you push forward here, you gotta get rid of the x variable. How do you get rid of a variable in life? You integrate it out. Hey, if you specialize it, you gotta choose one, right? So that's kind of very biased. But so the push forward here is the same in a Gisin sequence or something. You integrate out the fiber. So you would integrate now x like this, and that will be a function of y. For instance, if k were to be something like e to the minus I xy, this is literally the Fourier transform. And you would call these like the Fourier curve. Okay, so this is a sheaf theoretic version of that. It's a pretty standard construction throughout math. It's like pull back, push, pull, push construction. And that's exactly this convolution. That's exactly the way that you get this equivalence based on phi. Okay, so one thing I'm trying to highlight in here is that the important part about the generative variance is really about constructing this sheaf kernel. And the important property of this sheaf kernel is that it has a certain singular support. So I want you to think about this theorem as what the title of this paper is, which is it's a quantization theorem. Now, what is the word quantization here? So I can explain it to you. In the notes, I put a very precise reference of why this is called quantization. So this is called quantization already in analysis, like Ormander kind of version of FIOs. But the idea of quantization here is given a Lagrangian or given a Legendrian, I want to find a sheaf whose singular support is that one. And this is the first sort of foundational quantization theorem in that it says, given a Legendrian, namely the graph of your contact isotopy, I can find a sheaf that has singular support in that Legendre. So think of that as a very important starting quantization theorem that says, for Legendrians that come as the graph of a contact isotopy, there is a sheaf that quantizes them in this very particular way. And then once you have that, then you do this convolution with them and kind of follows that reasoning. Does that make sense? Okay, so how do you prove that? I mean, we can go over it in some other time, but the proof I would say is if you know the proof for generating functions being invariant, is exactly the same. So it's literally you mimic the proof of generating functions that Sikorov and company did back in the day. So it's not very complicated in that sense. If you've never seen that proof, it's not hard either. Like it doesn't require any massive machinery. So the way you do that is for t equals 0, you know what this should be. This should be the diagonal, essentially, because it's like the identity map. And so for the diagonal, you just find a sheaf by hand. It's like really straightforward to do that. And now you argue that as you move the diagonal a little bit, kind of no randomizer move is going to happen. So in the neighborhood of the diagonal, you're literally going to have like diagonal times something. Now the sheaf didn't care about the times something. So in a little neighborhood, you have still a sheaf that quantizes that. And now that you do a trick, you need to prove the way to do it. You need to prove uniqueness first. But once you've proved uniqueness, like assuming that this happens, it's unique. Then you do the trick that, okay, I do it for a little interval around 0. And now I moved a little bit and I do the same argument starting at the end of that interval, like slightly inside, but at the end, and I continue. So I'm saying this is very similar to generating functions because that's how you argue. You sort of do your generating function for a bit. At some point it stops and you say, okay, just go backwards a little bit and do the same argument starting with that one. And if you know it's unique, then it means they glue in the region where they overlap and then they continue. So that's how this paper proves this theorem, and that's sort of a pretty general way to establish that things are quantized, that they do have a generating function under Legendre isotopy, if the first one does, or in this case, that this also has a sheaf supported here, if this one does.
Broken geodesics.
Sorry?
They call some.
Is that called broken geodesics? Oh, okay. Yeah, I mean, maybe they're called geodesics because phi t could be the geodetic flow, and in that case, like maybe that's that. Okay, so I mean, it's a very beautiful paper. I recommend that you read it. This was kind of a very dramatic simplification of the paper, but that's kind of the intuitive idea here it works. Okay, so this is the first instance of a general phenomenon. So whenever you hear the word sheaf quantization, this is your first example where this is a non-trivial fact. And sheaf quantization at a basic level is saying, given my Legendrian, can I find a sheaf that has singular support in it, ideally exactly it? Another way to phrase it is, does that category contain anybody? Okay. And sometimes the answer is no, doesn't contain anybody. For instance, if you stabilize a Legendrian knot, or it's John defined in higher dimensions with Tobias and who else?
Sullivan, Mike Sullivan, yeah.
Mike Sullivan. Yeah. So the Legendrian stabilization in any dimension, if you stabilize there, no generating family, no sheaf, no anything is going to happen. So those guys cannot be quote unquote quantized. So the precise statement about sheaf quantization.
Is that true for any stabilization high dimension or just ones near cusps?
Any.
Okay.
Yeah.
I mean, ones near cusps make them loose, but ones away from cusp don't have to.
The ones that make them loose.
Okay, but they don't always have to be loose.
Yeah, stabilization. Sorry, I was thinking exactly about even
Okay.
preserving the formal class. Like
Yeah, okay, great.
Yeah. Okay, maybe to say a loose Legendrian in higher dimensions doesn't have a sheaf quantizing it, stabilized not in the lower dimensions. Okay, so this thing about the word quantization, again, we can talk about what it means, but for us, shift quantization means finding F such that the singular support of F ideally is exactly lambda. And here the input data is lambda. So the input is lambda. Okay, now a very first comment that's important is to say if a shift quantization exists, it's not necessarily unique. This is already obvious for the M Legendre. If M were a manifold with a lot of interesting local systems, who quantizes the M Legendre? That's who are sheaves that have no singular support, or any local system does. So already for the M Legendre, there's like this rich category of people that quantize them. Okay. So usually there's a refinement of that, and I'm going to talk about it in a bit, called the microlocal functor, where the refined shift quantization problem is given a Legendre lambda and a local system in it, can you realize a shift such that blah blah? That's a refined version of the quantization. So I want to give you one important theorem on that, in addition to that one, and then very quick sketch of one technique that people do use to quantize. So this is work of, well, originally the Viterbo, and then Stéphane Guillermo. This is independently Stéphane Guillermo. It's a very important case where you can quantize. So if lambda is a Legendrian in, say, infinity of M, standard complex structure, think of R2, that's fine, that would be not. And now, for now, let me just have no rep ports. Then it can be quantized. So that there exists a shift F such that the singular support of F is there. And it's not just that, you get some properties. So it's this statement plus F has good properties in that it knows the cohomology of lambda and things like that. So if you compute the endomorphisms of this shift F, you're going to learn things about the topology of lambda, their fillings, so on and so forth. Okay, so this was sort of in the direction, if you've heard about the nearby Lagrangian conjecture, towards that. So in shift theory, what you would think about is I have a nearby Lagrangian in some cotangent bundle. I can take the Legendrian lift of that, or I can transform it into some Legendrian problem. Maybe, sorry. Maybe let's do it this way. Let's do it again. So that then literally this is for the nearby Lagrangian. So if I have a nearby Lagrangian, it will be an embedded exact Lagrangian in a cotangent bundle. I can lift it to a Legendrian, and that guy being embedded translates into the condition of having no rep ports. And then what kind of things you want to say? You want to say any nearby Lagrangian in the cotangent bundle has the same homology as the zero section, the same homotopy as the zero section, the same banana thing as the zero section, right? And down the road, somebody at some point hopefully will prove it's isotopic to the zero section. But we're very far from that. So the idea is that one way to approach that would be to say, well, let me find a sheaf in the zero section that exactly quantizes, whose singular support is exactly that Lagrangian, which after quantified is this Legendrian lift. And then if that sheaf knows about properties of lambda, maybe I can compute cohomology of the sheaf and show that it's just cohomology of the zero section. And now if you don't like cohomology and you want homotopy or frame covariatism or other kind of invariants, maybe you can try to run the argument with more general coefficients, so on and so forth. And the current state of the art is, that the cohomology concept of the zero section is pretty standard. So that's maybe from the 90s. And somebody proved it was a homotopy equivalent to the zero section. So with the sheaf theory technique, Yermou was able to argue that. And independently, I think maybe it was Mohammed Abu Zaid and company were able to do that. And then Mohammed and Thomas Crack were able to improve it to simple homotopy equivalents. And very bit a bit, this obstruction vanishes, the other vanishes. I don't know, maybe in 5 years they can prove PL isomorphism or homeomorphism. And the big wall is difficult. And that's where nobody has any that we know. Okay, so that's the kind of result that we know of quantization. So the basic result of quantization is you can quantize graphs of contact homomorphisms and in families. the second important result is you can quantize nearby Lagrangians, the Lagrangian lists. And the things we will be quantizing is what in that blackboard? We want to be quantizing lambda, the Lagrangian on orange, and the Lagrangian filling L. If my Lagrangian filling is embedded, the quantization argument will run very similar to that. So this is just to know that a quantization exists. Now, because things will be very hands-on, I'll focus on very specific examples. You didn't need to know that your lambda like fits some kind of description. Sometimes you can just go by hand with the exotropy description of this morning and just find a sheaf yourself. So for those Lagrangian fillings, I personally will just quantize them for you by kind of brute force by hand. I'll just give you sheaves that do the job. But there is a general method that works. So the general method, and an idea that is pretty interesting. So a general method, it's called the doubling trick. So it goes under the name doubling trick. Some people are trying to change it or give it a different name. Some people are calling this anti-micro localization, like David Namler and Direction, they're doing that in their articles. There's a reason for that name, but this trick is really good. So for now, I'll just explain. So that's a trick that Guillermo uses, and it's used in a variety of contexts. Not only Guillermo used it, if you checked out the last paper of Abu Zaid, Guillermo, Craig, and Court. Anyway, that's the one that says that any around Lagrangian admits a twisted generating function. That is exactly the idea. So in fact, the doubling trick started in sheaf theory, and then they adapted it to generating functions. So that's one example where even if you didn't care about sheaf theory, it taught you a really good trick that then knows. So what is the very like 2-minute explanation? The elevator pitch in case you're having a job interview and somebody asks you, this is doubling trick. Okay, so here is the idea. Like suppose you have a Legendre and you have no idea whether it bounds, where it has a shift quantization, quote unquote bounds Lagrangian filling. The idea is it doesn't matter how bad your Lagrangian is. It could have a zigzag to be stabilized. What you know for a fact is that if you take the rep push-off, so if you take this guy, union its rep push-off, okay, so this guy will bound something. And well, something that has nothing to do with this. So for instance, if this was a trefoil, and I should do an example. Like if you take the trefoil in here, and you take the rep push-off, the rep push-off is going to be exactly a 2-component link that now has a filling, which is a cylinder. In fact, the rep push-off union, your guy always has a cylinder. And how do you see the cylinder? The cylinder is exactly given by these little guys, like these strands in here that are going like this. Does that make sense to everybody? Like, do you see as a smooth surface at least that bounces? I mean, the cylinder is literally the trace of the rep isotopy. You have the Lagrangian, and you just trace it. That's your cylinder. Okay, so that guy has a Lagrangian filling, Lagrangian cylinder filling, and this has nothing to do with the one-puncture fillings of this guy. Okay, so these guys fine. Wow. No, nothing to do with each other. A priori. Okay. So even if your guy was stabilized, the 2-component will have a Lagrangian filling. So the idea is to say, well, I want to find a Lagrangian filling, a sheaf, and I don't know if this guy has it, but this guy does have it. And the sheaf, how is it going to look like? It's going to look like 0, 0, K here, exactly mimicking this idea that all I need to take is this kind of strand. So it's 0, K inside 0, and then my K is everywhere inside. Like here, K, 0, 0, K, K, so on. Does that make sense? So that's the sheaf you start with, or the generating function, you would do the same thing. You would take a generating function with the double. And here comes the fun part. The fun part is now to say, well, what I'm going to do is I'm going to take the top copy, say, well, sorry, in this case, the blue one. So now take the top copy and push it up as much as you can. Just go as much as you can. Now, if there's no rep chords, what this means is as I move the blue up, there will be no point where the blue and the green as Lagrangians in R3 will intersect. So if there's no records, the blue guy can completely be separated and leave the green downstairs. So now what has happened is, under certain extra hypotheses, is you've now created a sheaf that looks like it's completely dealing with the green one. It has some stock in here, and then it completely deals with the blue one, and then you say, I forget about the blue. So now you've created a sheaf out of K. Obviously, because of the things in the previous board, every time you do a Rodemeister 3 or you do a Rodemeister 2, in order to push that, the sheaf on the green is going to significantly change. So even if you start with a sheaf that looks like K here and 0 outside, when I push the green guy up, the sheaf might acquire very interesting stocks and very interesting. Now, if my Legendre is not having, it does have records, it's not having this nearby condition, then this doesn't work, obviously, because I take the green copy, I pull it up, and at some point, boom, the Legendre will, the one component will be intersecting the other one. Now, in some cases, you can kind of still make it work. For instance, if the thing looks like a clasp move, and there's certain conditions on that clasp move, maybe you can still, like, okay, I'll do the clasp move and I'll keep going, and I still do get a sheaf. It's the same spirit in generating families. Okay, maybe I get an merged thing, but it's still unobstructed. There are some cases, for instance, like the case of a stabilized knot, where you must fail. Because if you were able to do that, then you would end up with your stabilized knot having a sheaf, which you know it doesn't. So in some cases, you can run the thing and still get a sheaf in this way, but in general, you know, this has to fail. So there's currently like no general theorem that says when you fail and when you don't fail. But maybe the rough intuition would be if this has a generating function, in some sense, the sheaf should exist and it could be built in that way. Does that, maybe it was a 5-minute explanation, but this is what the doubling trick does for you. Okay, and maybe it also illustrates something that is very apparent in when you answer word, which is this is maybe one way in which you can start to think that sheaves see a little bit of reports. You could maybe try to organize that every time you pull the thing, the pulling is exactly happening through a rep cord. So every time I kind of undo that, the sheaf contribution sees something about the rep cords. And I think, was it your first or second paper? One of the paper called like estimating rep cords makes that very precise. Yeah. Okay. Are we, maybe we'll learn something out of this. Okay. So,
Okay, that's why they need the no rate chords hypothesis, so that the doubling fits.
yeah. Yeah, so in the Guillermo's proof of this is exactly doubling trait with no records. Yeah, we generally use floor theory. You did like family floor before family floor was corrected. Which we're smaller. Okay, so the last technical thing I need to tell you, I promise it's the last technical thing, then it's going to be a lot of explicit examples. The last technical thing is going to be so-called microlocal functor. And I want to give you an explicit formula for it in the case of knots, but tell you a bit what it is in general. So in fact, there's a very beautiful link between the geometry of the category sheaf sub lambda and the geometry of lambda itself. So this is called a microlocal functor. And again, sheaf quantization sometimes means sheaf quantization with the data of the microlocal functor image. So in general, there exists a functor that we denote m sub lambda, and usually math frac m, from sheaves lambda on m to another category. Now, think about sheaves on m with singular support on lambda gives this thing, but there's another way to build a category with the same information that in this case, we denote new sheaf lambda of lambda. So without this is the so-called Kashiwara-Shapiro stack, which is like a sheaf of categories, not the global sections of the stack. Okay. So this might look very mysterious right now because I haven't not at all talked to you about this. But the point is, under certain conditions, so certain obstruction vanishes. And this is always true for the examples I will be doing, and things like rotation to your Legendrians with the Lagrangian fillings. All these obstructions do vanish. That's actually just equivalent to the category of local systems. So if you have a knot, this is just representations of the modules of the Laurent polynomial. And you have a length, it's more complex. So what is this in practice? So in practice for us, this is how you compute that guy. So in practice, for lambda and odd, it also applies for surfaces. But for this a not, this microlocal functor is computed by the microstock. By the microstock, so this mu sub x psi, and now x psi is in lambda. And specifically, when you have the exodromy presentation of your sheaf, is you have your sheaf in here, and you have your stock A, your stock B, and this is your map F, gives you the information of the sheaf. The claim is that the stock of the local system around this point, and therefore, because the local system in the neighborhood of it, it's exactly going to be, so microstock is the cone of this map. So it's the cone of F. So in practice, the way you're going to be computing microstocks, for instance, if you have something like that, you have like 0, k squared, k. The local system literally is in here, the point in here gets the stock, the cone of this map, which is k. So in here, it's also going to be k. So now I have a local system, which is k everywhere. Does that make sense? So that's like in practice computation. I mean, there's a theorem that says this thing can be computed like this thing, and then in practice, you just do it like. So the cones, having the exodromy description of this morning, the cones of those maps that we described this morning have meaning, have intrinsic meaning, and they're precisely microstock. Okay? Okay, a little technical aside. Why do I work with digi-categories, or why do I think digi-categories are better suited than the classical derived categories? So if you read the book of Kashiwara-Shapira, those are entirely within derived categories in the classical setting. You have homotopy categories and you portion by quasi-iso, so on and so forth. But it doesn't have the digi enhancement. So a well-understood issue with derived categories, there's several of them, they're not stacks, blah, blah. But one specific issue is cones are not functorial for classically derived categories. So if anywhere down the road you're going to be taking cones, you want them to be as functorial as possible. And here I'm giving you a very good reason to take cones in general. So you want to make these things functorial, and in digi enhancements, things are functorial for cones. So that's yet another reason. So Radameister one forces you to work with some sort of complexes. You could say, I'll just stick with derived categories. That's fine. But there's a number of reasons, this being one of them, that tells you it's better to use the digi enhancement because you're going to get more functoriality. Okay, that's a technical comment, but maybe it's relevant. It's like, well, why would you go like to that pain in order to do all that? Okay, is that clear so far? Any questions on that? Or so?
Can you repeat what the microstock was?
The microstock was the cone of the sections over the whole thing, restricted to the sections downstairs when the codirection is exciting. And shifted by one. It's the same as a stock, but it takes into account the direction. And then it's the limit, co-limit, overall the use like that. That was
This is what
microstock.
we're computing.
Yeah, and I mean, you just literally take a definition, unravel
Yeah.
like James's recitation or what I did this morning, and then this map is just F.
Okay.
All right. Okay, so I'm gonna start doing examples of sheaves. And tomorrow I'm gonna be more precise about what I mean by the model I of sheaves. But the lectures now are gonna shift towards a more sort of explicit class of examples and computations. And the idea is that we want to make sense of what are Lagrangian fillings that do exist. How do they fit into a certain space that I'll be referring to as the model I of Lagrangian fillings? In which sense it is a good model for the model I of Lagrangian fillings, and in which sense we still, we're aware that it has some shortcomings, some things we cannot prove. But before I do that, I just wanted to give you a bunch of examples to get a better sense of what kind of sheaves we're dealing with. Tomorrow I'll do like all the proper definitions and specialize to all the examples. So let's just draw a bunch of sheaves in here. This is one example in here. And now I want to draw a bunch of examples after the Hovling. and then the two Chicano guys. Okay, are you all on top of what Lenny said yesterday about what the accommodation variety was for this guy? Lenny said yesterday, this is 1 plus x plus 1 plus yz equals 0. Do you remember that? Okay. I think I'm trying to use the same coordinates that you just did. Lenny said something like that. It should start exactly that, but yeah, okay. And then we're gonna have the other Chicano guy looks like this. Okay. And I don't know if anybody remembers, but I think it was something like 1 plus xy equals, right? Have the notes. Okay. Okay. This is the same as C star. And this is exactly, that's the same as C squared minus what's gone. All right, so let's just do a bunch of examples of shifts in here. Let's see. For the unknown, what choices do I have? If I didn't have the Rademeister move, and I'm always going to force 0 outside, and I'm always going to force the microstock to be exactly K. They're called pure shifts. So pure shifts and actually simple, if you want. So 0 here, I have K. That's with the Maslov potential given by 0 here, 1, 1, 2. So 0 and K. If I was done, that would be the only shift that I have. So that's the example that James did. And then otherwise, you're going to have in this case shifted y1. But as we said, by the Rademeister move, that should not make any difference. So the category should be exactly equivalent, and there's no choice for these maps at all. Okay. Now, what about the Hopling? So these are two presentations on the Hopling. As an example over here. I could do 0 here, then K, 0, and K. And now I find some interesting conditions here. If I look at this crossing, it's 0, K, K. Here I gotta put K squared. And then I'm going to have also up here 0, K, K, and K squared, right? With the maps going the other. So how do I translate that into kind of a linear algebra problem? Well, there's one map here, which is a line. There's another map here, which is another line. So these are two lines in R2 or in C2. So there are two lines in the plane, and they must be different, right? Now, I also have extra two lines. So this map and this map, I could take the kernel of these two projections into K's, and that's going to give me two extra lines, right? Now, because this has to be the identity, it couldn't be that this line coincided with the kernel of that one, because otherwise, this map would have the identity, would be 0. So this line has to be different than this one. The crossing tells me that this line is different than this one, and the cusp condition again tells me this thing. So we see something that I already discussed a bit for the trefoil. We see 4 lines, L1, L2, L3, L4, all lines in K2. So these are lines. And the condition is that Li is different from Li plus 1 cyclically. So this is happening cyclically. And this is like modulo the action of GL. Okay, does that make sense? I promise tomorrow and as we go on, I'll keep talking more about this space. Does anybody have a sense of what this space looks like? So exercise for tomorrow or maybe for the group. If you take this space and you quotient by the sister action, which sends y to ty and z to t inverse z, the quotient of that space is exactly this space. In fact, before quotienting, this space is exactly this space. You want me to prove that, or I can probably do that in 1 minute. That's an exercise. That's it. Okay. I rested yes, Carlani, who said that's an exercise. It's fun. Okay, exercise for the group work, and otherwise I can do it then. How about that? This space of line can be expressed as this. All right. Now, how would I see the shift space? Well, by invariance, they gotta be the same. Here it's much more apparent, maybe. Here I have K, 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 so here are the 3 lines, and then the 4th one would come from here. And you can continue this game and present the top link in a more elaborate way. For instance, you could do 1, 2, 3, 4 crossings in here like this, and then do this. And now here you're going to have 1 line, 2 lines, 3 lines, 4 lines, and the cusp conditions are going to tell you that this determines the kernel of this, which determines this. So this line has to be the same as this one. So 4 lines, and the crossings here and here and here and here tells you they have to be different. So yet another presentation of the half plane, yet the same shift space. But do we start to get a feeling for this game? Like how do we use a lecture from this morning to get this kind of things? Okay, so last comment is I have the two Chekhov nodes in here, the two representative of F52s. They're not legend isotopic, but we don't know that for the second. Okay, it's supposed to kind of do that in case examples in the 20,000 paper. What do? Well, 0, k, and now because of this example, we know that locally it's got to be k shifted by 1. It's got to be k shifted by 1. This is going to be k shifted by 2. This is going to be k shifted by 2. And now locally, what does this look like? This looks like exactly like this discussion. So if I put 7 twists on the right, 7 twists on the left, as long as I put the same number, the shifts are going to coincide. Then I'm going to have this model. So what do I'm going to get as the model I of shifts, as the space of shifts with these support conditions? I'm going to get the space of 4 lines modulo this. Which, as I said, you could, as an exercise, check that it's in the equal lengths. Okay. So that, it's not just for M52 and it twists not built that way, you will get exactly the same. So this is a nice example also where two distinct Legendre knots are not even as a topic, but the shift might coincide. Okay. So what's happening in here? What's happening in here is that the shifts are all wrong. So here the shift is 1. Here, if you don't have the same number, you're going to shift by 2 and then 3. And now the conditions here are going to be much more subtle. So here you're going to have, you can think of these as having 0 here, or you can think of it as having the complex, the acyclic complex here. Maybe it's just a bit more helpful, but there's an acyclic complex. And now you're going to figure out what those conditions are in here. And exercise for today, good thing in the group work, check that the conditions that you're getting here are not 4 lines with this condition. You get some other conditions about lines and things and places, but they're very different from that. You get a unique C-star choice, and that's exactly this space thing. So that would be a shift theoretic way of approaching that these two nodes are not Legendre isotopic. I compute the category of shifts, quote unquote, and I'll make that precise tomorrow. You take the modelized space of objects, they're just plain different. And they're like reasonable varieties. It's not completely out of control. So we'll be doing all of that with positive grades a lot, and we will shift the discussion towards Lagrangian fillings a lot. So I'm going to focus on positive grades from now on and Legendre closures with positive grades, and then do an in-depth study of their Lagrangian fillings. And whatever I'm saying there, you can try to adapt to things like this. All right. Any questions? Okay, then I'm done, and I'm looking forward to one nuance lecture, which is next.